Okay, so although I was drawing the dotted curve, the solution exists only for this shaded region. Okay, I have plotted the dotted curve only for the free particle, but we have considered the intermediate electrons, that is not free, neither free nor completely restricted to the one dimensional infinite box. Okay, so for the intermediate case we can get the bands like this. Okay, and the mathematical formula of the Brillouin function is can also generated from k is equal plus minus n pi by a, that I have shown here. Now let us move on to the next thing, that the number of possible wave function in a band. That is, in if we concentrate a single band, okay, the number of possible wave function within the band. So in the total lattice we have considered the a plus b is the lattice parameter considered here. So the total number of total length of the lattice will be n number of lattice points into a plus b. This is the total length of the lattice, and we know that psi x should be periodic, psi x plus L, which was our assumption from the Bloch's theorem. And from the Bloch's theorem we can also say that psi kx is equal e to the power ikx ukx. Okay, where ukx is the periodic function. And if we place these in this equation, we can get e to the power I kl should be equal to 1, which means kl is equal to pi n. So n is equal kl by 2 pi. So in n uh, n amount of what we can say, n number of, for n number of lattice points, we can get the number of band kl by 2 pi. For dn number, what we can get, we can get l by 2 pi into dk. This is the number of possible wave function within dk, and this is the number of possible wave function within k. So if we get the total, if we want to get the total number n, what we can say, it is the integration of the elemental decay. So L by 2 pi, what we are interested, we are interested in the first band, how many wave function, how many number of possible wave function in this first band. So the first band ranges from, although I am showing this, you can for better understanding I have, okay, I am going to plot the actual band. The actual band is like this, from this. So the range of the k, range of the k is minus pi by a to pi by a for the first band, the number of possible wave function in the first band. This is equal to L by 2k, sorry, L by 2 pi, pi by 2 pi by a. So L by a. So L is equal NE. Again, from this, for b tends to 0, that is the case that we have considered earlier. Where? Okay, yes. For the case b tends to 0, what does it mean? B tends to 0 means this small width that we have, this b tends to 0 means this small width is so negligible that we can neglect it. If we neglect it, then what does it result? L is equal n into capital A. Again, what we have obtained for the first case, L is equal NA. So NA is equal NA and the n is equal capital A. What does it signify? It gives us a very important conclusion that the number of wave function present in a band is nothing but equal to the total number of unit cell within it. Okay, So if we consider the spin of the electron, then one state can possess by two particles, so maximum of two particles. So this is nothing but the number of electrons in a band is 2n, if we consider the Pauli exclusion principle. Okay, now the allowed electronic energy state thus fall into the bands which are separated by the region known as forbidden energy gaps, and the number of available states in the band depends upon the number in present, number of the atoms present, and due to the spin plus minus half of the electron, the total number is 2n. That is 2n electrons will be required to fill the first band. The two bands of the importance of semiconductor terminology are valence band and conduction band. What does it signify? Let us discuss. The lowest completely filled band is called the valence band. The lowest completely filled lowest band. That is like this. You can get many number of bands. The lowest number of bands which is completely filled. Suppose this band is completely filled. This is the lowest band which is completely filled. We can term is as a valence band. And the next succeeding band is known as the conduction band. And the basic properties of semiconductor is that the valence band and conduction band separated by very small amount of energy gap, which is known as the forbidden energy gap. For silicon it is 1.1 electron volt, and for germanium it is 0.74 electron volt. So that one can excite the electron from the valence band to move on to the conduction band, so that a vacancy or hole is created inside the valence band, and the electron gets transferred to the conduction band, from where it can again back to the valence band and creates some emission, which is the basic principle of LED. Okay, so in silicon and other certain elements like germanium, the energy band gap is very low, like 1.1 and 0.72. And for diamond, that is the insulator, the band gap between valence band and conduction band is very high, nearly about 6 electron volt, which is located nearly about 2s and 2p shell. If we concentrate on the atomic structure, then we can get this type of uh, what we can say, this type of values of the orbitals. Okay, now we have discussed, or we have defined, the conduction band and valence band. Now what is Fermi level of the semiconductor? The Fermi level generally generally used to be defined by EF, and it is present between the valence and conduction band. It is the highest occupied molecular orbital at absolute zero temperature, and the charge carriers in this state have their own quantum states and generally do not interact with each other. When the temperature rises at above the absolute zero, the charge carriers will begin to occupy above the Fermi level. Okay, the Fermi level lies within the forbidden gap, and when we heat up, when at absolute zero temperature, it is the maximum energy level that can be occupied by the substance, and if we apply a certain amount of energy, then it can get back to the uh, conduction band. This, and depending upon the extrinsic intrinsic property and the doping, the dependency of Fermi level, the position of the Fermi level varies. That is another issue, and we can mathematically also derive this. But the most important thing here is, now we can represent the energy level of valence band and conduction band mathematically. How? The conduction band, at first we can write the conduction band as a function of k equal to the band gap Eg plus h line square k square upon 2 me star. What we have done? Excite the electron to this. Okay. So what is this? the energy occupied by the electron, which is this, where m star is the effective mass of the electron. What is effective mass? Inside the crystal, like the ordinary electronic mass, inside the crystal the electron have certain different mass, which is known as the effective mass, which results out due to their motion inside the crystal. Okay, and by the analogy of the free particle of electron, where the energy is h line square k square by 2m, we can represent the energy inside the crystal of the solid state device. The energy possessed by the electron is h line square k square by 2m star, where m star is the effective mass, and it has, from the definition, the value m star is h line square by d2v dk2. Okay, that we can derive also, but if you required, we can also derive the effective mass formula. So let us do this job. Suppose the electron is considered inside the crystal is acted upon by some electric field E. So what we can do, we can compare the force E to be equal to the um, E, this is the force, and if we consider the energy, this is like this, so that we can get D is equal minus E v dt. Now, what we can know, the velocity of the electron inside the crystal. Velocity of electron inside the crystal is nothing but the group velocity. Group velocity is d dk, and E is 2. For free particle, let us assume, then we can get the analogy. E is equal h line square k square by 2m from free particle analogy. So d dk results out to be h line k upon 2m to this. 2 gets cancelled out, h line into h line k upon m. What does it mean? It means simply velocity, v. So v is nothing but 1 by h line d dk. Okay, so we can get acceleration out of this. Acceleration is nothing but dv dt. So 1 by h line d dk into dk dt. We have applied only the chain rule. Now d decay, E and k dependency are known to us, but k dependency on time is not known to us. For this we have to consider the phenomenon of this. So d is nothing but minus E. This is the electric field applied on the motion of the electron, and v is the velocity possessed by it. It is the time interval. So we can uh, place the value of v here. What is this? 1 by h line d dk. So d, okay, d in the left hand side, e, v is 1 by h line d dk into dt. D we can cancel out, so dk dt has obtained e h line d e d dk dt, and negative sign appears here. Okay, so dk dt gives us this value. Now we can avoid this negative value. This is only due to the charge of the electron. We can avoid and take the modulus of it. Okay, now dv dt means 1 by h line d2e dk2 dk dt. So we can place the value of dk dt 1 by h line d2e dk2 dk dt means e upon h line. So 1 by h line square d2e dk2 into e. This is the acceleration. Now for a free particle, for a free electron, what we can say, this is the force. Okay, if we consider the negative sign also, it gets cancelled. So consider this negative charge. So if we consider the free electron, then this is the force, which is nothing but mass into acceleration. So we can say acceleration to be equal to minus e upon m. So here also the mass is minus E by H line square divided by, okay, this d2E dk2 inverse. So from the analogy, this is equivalent to this term. This is the mass. This is the mass of the electron for the case of moving inside the crystal. So from the free electron analogy, we can get this type of value of the mass of the electron when the electron is concentrated within the crystal. This is known as the effective mass of the electron and is defined as the H line square upon d2E dk2. So the conduction energy of the conduction band energy can be given by ECK, EG. ECK is equal EG plus H line square k square upon 2 m star. And the valence band energy can also similarly given by H line square k square by 2 mH, the effective mass of the holes, like the similar analogy, but by default definition it is negative. By default definition it is negative. Okay, the valence band is again represented by the standard inverted form because we are interested only in the region close to the top of the band, so that we can represent, earlier we have represented the bands like this. So if I copy this, if we copy this, just a minute, yes. So this was the earlier band diagram. For clear cut view you can, sorry. Yes. So mm, yes, yes. This was the earlier band diagram, but now due to the mathematical forms as represented by 1 and 2, let us give it equation 1, let us give it equation 2. So from 1 and 2 you can clearly mathematically represent this. So if we represent this to be k line, and energy can be given by this. This is parabolic in nature, separated by some spacing Eg, and this is the equal to 0 line. Okay, so for symmetry we have considered this to be negative. Valence band is negative, so this is nothing but H line square k square by 2 m star plus Eg, and this is minus H line square k square by 2 mh star. This is the conduction band, this is the valence band. Earlier we have represented these by like this, but actual figure of the valence band and conduction band is like this. Now you can clearly understand why we have mathematically defined the valence band like this, because we are interested to the top of the band and lowest of the conduction band. Okay, now the primary band structure parameter are thus the electron and hole masses. That solely depends the energy, that you can see from the definition given by the mathematical formula. Okay, now depending upon this structure also we can classify the semiconductor by direct band gap and indirect band gap. This is a case where the top of the valence band and lower point of the conduction band, that is minimum of the conduction band, lies in the same k lines. But in the silicon, what is done, suppose this is the minimum of the conduction band, this is also the case, this also case we can get, this is the ideal case, but this is also case we can get. but the more important thing is the lowest point of the conduction band and the highest point of the valence band. This, sorry, like this. This is the maximum point and this is the lowest point of the conduction band, but these are not placed in the same K line. This is placed in some another K value. So we should have to this and this for, we should have to go like this and this for the excitation of the electron. So due to these extra path, some phononic interaction is there. We will study later the fact like this. So this is known as the indirect band gap semiconductor. Indirect band gap semiconductor. Semiconductor. And this is direct band gap semiconductor like gallium arsenide. So gallium arsenide is preferred to be the constructing material for the LEDs because energy dissipation is very low here. That's because only it is easy to excite the electron from the top of the valence band to the lowest point of the conduction band, but it is a little bit more energy required for the similar transition. Okay, so these are the things that we can get from the band theory. And I again repeats that this lecture is incomplete without the previous lecture. So at first you have to go to watch the previous video, which is readily available in the YouTube by some 3 to 4 months ago. Okay, I have delivered this, and this is the lecture which is the outcome of the previous theory that we have discussed, the chronic penny model, which is very simple but little bit more mathematical. So you have to understand and do the mathematics very carefully. This is nothing but the application of the quantum mechanics, and this is the Bloch's theorem which we have applied in this lecture also. So now this total theory is complete, and depending upon this band gap energy, depending upon this forbidden energy gap, there are the classification of the metals, solid semiconductors and insulators. Okay, thanks for watching. If you like this session, then you can hit the like button also and share this lecture with your close friends as well. Thank you so much.